My name is Junya Hoshi. I will now explain the basis of passive sampling, example of sampling rate calculation, and practical examples of sampling rate, sampling, and extraction from solvent tube. There are two commonly used methods for measuring VOCs in air, active and passive method. A brief of description of the advantages and disadvantages of each is given first. Firstly, the active method is explained. The absorption tube method is used as an example of one of the active methods. The advantages of the active method are that it is less susceptible to environmental influence such as temperature, humidity, and wind, uh, has a higher concentration rate and allows sampling in short time. On the other hand, it has disadvantages such as complicated pump operation, which requires workers to visit the site for sampling, high measurement cost, and various limitations due to the need for pump and power supply. Passive methods are described using the diffusion tube method as an example. The advantages of the passive method are the sampling can be carried out by simply hugging the sampler at a measurement location, making it easy for anyone to use. In addition, the method doesn't require a power supply and less expensive to measure than the active method, allowing simultaneous observation at multiple locations. However, it is less sensitive than the active method, making it difficult to sample ambient air in short time. When calculating concentration by passive sampling, a sampling rate is required, which is a coefficient for converting the amount of the substance of absorbed on passive sampler to an atmospheric concentration. The ambient air concentration using the passive method is calculated using the following equation, where uh, C is the measured air concentration, MD is the absorbed amount of the analyte collected by passive sampler. MD is the amount of analyte in unused passive samplers, which is a blank of the sampler to be used. Then T is the exposure time of the sampler, and SR is the sampling rate. The sampling rate can be determined by a parallel measurement of active and passive method in ambient air sampling, 1, or by calculation, 2, or by exposure test, 3. When active and passive methods are used in parallel for ambient air sampling, the sampling rate can be easily obtained. However, the sampling rate obtained by this method may differ in different sampling environments due to difficulties in controlling temperature, humidity, and wind speed. The versatility of the sampling rate obtained in this way is therefore limited. The method of obtaining a sampling rate by calculation can be obtained by fixed diffusion principles, and existing reports show good agreement between calculated and actual values. But uh, it is difficult to accurate, uh, accurately determine the diffusion range, which is a necessary parameter for the actual calculation. This can only be obtained by substituting experimental or sampling results into fixed diffusion formula, or by guessing from the structure of the passive sampler, so the calculation method is not widely used. Method for determining this by exposure testing are described in the Japanese standard JIS and ISO 16107, and the experiments can be conducted in accordance with those standards to determine the sampling rate of passive sampler em- in an environment with controlled temperature, humidity, and wind speed. However, it is necessary to prepare a large chamber and compressor for the test, which involved high cost for experimental equipment. In addition, uh, complicated experimental operations are required, such as sufficiently stirring the air in the large chamber and conducting exposure tests when the air in chamber is uniform. The sampling rate is calculated using this formula. Here, the sampling rate calculated at the Tokyo Metropolitan Research Institute for Environmental Protection using power measurement of canister method and diffusion tube method or passive method for ambient air. The canister method was used as a reference measurement. As shown in the graph below left, the x-axis is the product of the canister method reading and the exposure time, and the y-axis is the volume collected by passive samplers. The slope of the line is the sampling rate. This time, two passive samplers, one from Spherical and one from Shibata, were used to check the differences between the manufacturers. As a precaution, when calculating the sampling rate using this method, the range of variation of the concentration in the air is required. The following are examples of parallel sampling rate measurement and the result. The study was conducted on the roof of the Tokyo Metropolitan Research Institute for Environmental Protection in Koto, Tokyo, Japan. The dates are 20 to 27 July 2022, and sampling time is 24 hours. Canister sampling was followed by cold concentration and DCMS analysis after correction, while diffusion sampling was followed by extraction with carbon disulfide and analysis by DCMS. An example for benzene is given here. For benzene, uh, both the spherical and civet samplers show a better correlation with the canister method. This indicates that for both samplers, the diffusion sampler is able to follow the changes in atmospheric concentration with the same accuracy as the canister method. The slope of the line obtained is sampling rate. So the uh, value of sampling rate is varies from manufacturer to manufacturer. Next are examples for toluene and ether benzene. Both spherical and civet correlate well with the canister method for those substances, and good results are obtained for calculating sampling rate. The next example is for the rain. There is a good correlation with the canister method, and both spherical and civet have a good measurement result for calculating sampling rate. The sampling rate obtained in this parallel test were compared with the manufacturer's calculated sampling rate. The sampling rate for benzene and toluene, spherical toluene, match the manufacturer setting, but the sampling rate for ether benzene and xylene differed from the manufacturer setting. It is better to check which sampling rate is more realistic for the location to be monitored, uh, based on the actual local atmospheric concentration. Also, the civet sampling rate was generally higher than spherical sampling rate. Suggesting that civet may be potentially more sensitive to measurement than spherical uh, when the two are compared. I will now discuss how to actually sample with passive sampler. Using the civet sampler as an example. First, remove the small bag from the large bag containing 1 dozen samplers. Each small bag contains one sampler. Next, sampler is removed from the small bag. Sampling begins when the sampler is removed from the small bag. Therefore, the sampling start time should be recorded as the time when the sampler is removed from the bag. Wear gloves when removing the sampler to avoid contamination. Attach the sampler to the clip inside the shelter. Uh, Pull the string and place the sampler inside the shelter. Office clip may be used in place of the sampler specific clip. And place the shelter at the sampling point. Clip it where it can be hung, then roll up the string and fix in the place. If string is wrong, it can be agitated by the wind and become upside down or get wet from the rain. So roll up. When the sampling is complete, press the sampler back into the original small bag and then back into the large bag. Wear gloves during collection and operation. Sampling time is the time between removal from the small bag and return to the small bag. Record the sampling location, data of collection, and sampling time. Records can be written on the bag, or you may also make a field book to record the data. Uh, don't use magic pen when making this record, as VOCs may contaminate it. Use a pencil to write the record. Once samples are collected, you should be refrigerated or frozen until time of analysis. The following section describes how to collect samples from the solvent in the sampler. First, remove the solvent from the sampler. Use sprayer to slightly deform the aluminum ring at the top and bottom of the sampler so that the PTFE plug can be pulled out. At this point, place a piece of powder paper over the aluminum foil to collect any spilled solvent. Remove the PTFE plug and remove the polyurethane from inside. Next step is to extract the sample. Turn the tube upside down and place the absorbent inside the vial. Here, considerable amount of absorbent has adhered to the inner surface due to electrostatic. It is recommended to use an electrostatic remover to remove this successfully. Place the carbon disulfide in the vial and stir until the bubbles disappear. Leave to stand for 2 hours. Transfer the extracted supernatant to another vial. Use a pass-through pipette to transfer the supernatant to the vial containing the insert. It is then analyzed by ZCMS. Next, I have shown an example of the analysis conditions. Those conditions are the conditions I used for my analysis. Standards are created from standard 0 with using only internal standards to a concentration of 1000 nanogram per milliliter of each substances. However, due to the low environmental concentration, in most cases I use data up to standard 5 to construct a calibration curve. The following are examples of chromatogram and calibration curve from the analysis. The chromatogram shown above is for a mixed standard solution containing 500 nanogram per milliliter of each substances. Note that the retention time from 7.6 minutes to 9.5 minutes is the time during which a carbon disulfide used as extraction solvent is eluting and the ion source is turned off during this time. Therefore, VOCs eluting during this retention time cannot be measured under those conditions. As an example, the chromatogram of standard solution benzene and the chromatogram of ambient air sample and calibration curve are shown. The chromatogram of both standard solution and ambient air sample for benzene are good shape. The calibration curve of benzene is also highly linear, but an intercept can be seen in the calibration curve made with carbon disulfide solvent. This is considered to be a blank concentration of benzene present in the solvent. The chromatogram and calibration curves for toluene and ethyl benzene and metal plus paraxylene are shown next. Again, the chromatogram are well shaped and the calibration curve are straight. No intercept of the calibration curve was observed for toluene and metaparazylene. Finally, I would like to give a summary of measurement with passive samplers. First, passive method, especially a diffusion tube method, have the advantage that they are easy to handle and don't require a power supply. However, a sampling rate is required for each individual substance. Secondly, our tests show that there is no significant difference in measurement accuracy for BTX between the two passive samplers from spherical and Civata. Next, parallel testing with canister method showed that the sampling rate calculated in real atmosphere for some substances had values that differed from those set by the manufacturer. It would be necessary to check the sampling rate at the monitoring site. Finally, for BTX, the peak shape of the DCMS measurement is good and the calibration curve is linear. However, it should be noted that there is an intercept in the calibration curve for benzene. This is the end of the program. Thank you for watching.